Assalamu alaikum. My dear viewers, ever wondered how scientists measure the tiniest distances or the vast expanses of the universe with impeccable precision? It's a question that leaves many minds curious and eager to explore. The sheer scale of the universe, from the microscopic to the boundlessly expansive, calls for measurement tools and methodologies that extend far beyond conventional scales and rulers. Have you ever paused to think about how scientists might accomplish this incredible task? One might ponder, do they use some sort of advanced laser technology, or perhaps a complex web of mathematical algorithms? While these hypotheses aren't far from the truth, the reality is steeped in a principle as old as science itself: wave interference. And in the realm of precision measurement, one technique reigns supreme, a technique known as interferometry. Interferometry is a field that has proven to be of inestimable value in a plethora of scientific and technological endeavors. It is a powerful technique that employs the interference of waves, from light to sound and everything in between, to extract precise measurements. It's not as daunting as it sounds. Simply put, interferometry involves combining waves in a way that the resultant pattern provides highly accurate distance measurements. Fascinating, right? From measuring microscopic particles in cellular biology to gigantic astronomical bodies light years away, interferometry has revolutionized our understanding of the world and the universe around us. It has pushed the boundaries of science, enabling us to peer into the shadows of the quantum realm and the farthest corners of the cosmos with a precision that was previously unimaginable. Welcome to the fascinating world of interferometry, a powerful technique that employs the interference of waves to extract precise measurements. Interferometry, at its core, is a method that superimposes waves to investigate the pattern they form when they interfere with each other. This scientific technique, which may initially strike you as complex, is best understood when broken down into its basic components. To begin with, it's crucial to understand the concept of waves. From sound to light, waves are ubiquitous in our daily life. They are essentially disturbances that transport energy from one point to another. When two or more waves meet, they can interfere with each other. This interaction forms the basis of interferometry. Interferometry, in essence, superimposes these waves. Imagine two small stones tossed into a still pond at the same time. The ripples they create will eventually meet and either combine to form bigger waves or cancel each other out. This is a simple example of how waves can interact and interfere. Interferometry uses this principle on a microscopic scale. It ingeniously merges waves and studies the resultant pattern to uncover information that would otherwise remain hidden. Technically, this process involves splitting a single wave source into two, allowing them to interfere, and then observing the interference pattern. Applications of this method span across various fields such as physics, astronomy, biochemistry, and more. It's instrumental in studying cosmic objects, analyzing molecular structures, and even improving the vision of optical telescopes. Despite its wide-ranging implications, interferometry hinges on a rather basic principle: superimposing waves to study the interference pattern. Although it may seem daunting at first, interferometry can be simplified into a sequence of logical steps. Through careful observation and analysis, it opens up a world of knowledge previously inaccessible. This process may sound complicated, but in reality it's a series of simple steps. First, consider a wave. This wave can take many forms. It could be a wave of light, shimmering and dancing as it travels from its source. Perhaps it's a radio wave, invisible to the naked eye, yet carrying messages across vast distances. Maybe it's a sound wave emanating from a strummed guitar or a spoken word, reaching our ears with its distinctive tonal quality. Or it could even be a wave of matter, such as those that ripple across a lake. When a stone is waved, whatever its form, possesses a property we refer to as phase. The phase of the wave is akin to its heartbeat, a steady rhythm that keeps the wave alive and moving. It's a property that is defined by its source, a unique signature that differentiates it from other waves. It pulses in a rhythm that can be measured, analyzed, and understood. You might think of the phase as a wave's DNA, a fundamental characteristic that sets it apart. Now let's engage our minds further and imagine taking this wave, this pulsating energy, and splitting it into two separate, identical waves. We can do this using a device known as a beam splitter. This splitter acts as a kind of mirror, reflecting half the wave and allowing the other half to pass through. We end up with our two waves, each a mirror image of the other, each carrying the same phase, the same heartbeat. These two newly formed waves now commence their journeys, though they travel on different paths. One wave might proceed straight ahead, unimpeded by obstacles, racing towards its destination. This wave, for the sake of our explanation, we'll call the direct wave. The other wave, however, takes a different route. It embarks on a detour, a longer, more winding path that takes it around corners across vast expanses. This wave, the indirect wave, travels a more complex path, and its journey is filled with obstacles and diversions. Finally, these two waves, one direct and one indirect, diverge from their common point of origin. The wave speeds on a straight path, while the indirect wave embarks on a detour. This divergence creates a beautiful dance of physics, a testament to the complexity and wonder of the universe. But remember, each of these waves, though they travel different paths, began as one. One might go straight ahead, while the other takes a detour. After their separate voyages, these twin waves find their way back to one another. Similar to siblings separated at birth, they've each faced unique trials and tribulations. Even though they both sprung into existence at the same time, in the same place, and started their journeys with identical phases, their experiences along the way have changed them. Their paths diverged, with one wave traveling a more intricate, twisted route, while the other followed a more straightforward course. Due to their diverging paths, one of them has traversed a significantly longer distance. In the vast open sea of space, distances can drastically change a wave's phase. Time, the unyielding opponent of all entities, has also acted differently on these two waves. The distance, coupled with time, has likely caused the two waves' phases not to match anymore. This is where the fascinating science of interferometry comes into play. It's like a grand reunion of these two long-lost siblings, filled with uncertainty and curiosity. As they return from their distinct journey, they finally reconnect. When these two waves meet, they create a spectacle of nature. They interfere with each other in a dance that is both chaotic and harmonious. If their phases are still aligned, they add together in a beautiful and captivating display of unity. They combine their strengths and energies to form an even mightier and more potent wave. This strength in unity is what physicists and scientists refer to as constructive interference. It's a triumphant reunion, an affirmation of their shared origins and kinship. But if their phases have fallen out of sync due to their different paths and experiences, they act against each other. They cancel each other out, reducing their collective strength to a mere whisper of a wave. This weakening of power is what's known as destructive interference. It's a somber reminder of the consequences of differing paths and experiences, even among the closest of twins. But if their phases are out of sync, they cancel each other out, resulting in what's known as destructive interference. By observing this interference pattern, scientists can make incredibly precise measurements. If the distances the waves traveled are known, the difference in their paths can be calculated. If the wavelength of the waves is known, even the tiniest changes in the path difference can be detected. Interferometry has applications in various fields. It helps astronomers measure the size and distance of celestial bodies. It allows engineers to test and perfect optical components. It even aids in detecting gravitational waves, giving us a new way to explore the universe. To recap, interferometry is a technique that uses the interference of waves to make precise measurements. It involves splitting a wave into two, letting them travel different paths, and then reuniting them. The resulting interference pattern, whether constructive or destructive, provides valuable data that can be used to measure distances both incredibly small and unimaginably large. Remember, the beauty of interferometry lies not just in its precision, but also in its versatility. From the tiniest particles to the furthest reaches of the universe, interferometry helps humanity measure, explore, and understand the world and beyond. So, the next time you gaze at the stars, remember the sophisticated technique that helps us understand them better: interferometry. Thanks for watching, share our videos, and don't forget to subscribe Quest and press the bell icon so that you receive notifications whenever we upload our content.